Thank you, Eric. I want to thank the previous two speakers, Bill Shamiris and Eric, for really setting the stage nicely. I also want to thank my colleague, Dr. Christina Ficchini, as the reason I'm here, her invitation. What I wanted to talk to you about, what is the problem with respect to climate change? Just to get to the bottom line, basically what I wanted to show you today is data and inferences to the effect that we have already put enough greenhouse gases that surrounds the planet like a blanket, and we're committed to a warming which will be large enough to push the system beyond several thresholds for making iconic changes, and I'll talk to you about what those changes are. Being an atmospheric scientist, I start with the perspective. If you look at the atmosphere, when you go out and look, it looks vast, and the impression you get is there's not much we can do to this. It's so huge. And look at that, just a thin shell. It's in that shell we are dumping billions and billions of tons of pollutants. And what the sources are, we know all of them: smokestacks, automobiles, biomass burning, agriculture, and the last you see is my grandmother's kitchen from South India. So the woman there, she's not my grandmother. Her father, her father used to tend the village, farm of my grandfather. So the question is, why should that woman, when it's sitting in that kitchen, worry about what car we are driving in Davos? Likewise, why we here should worry about what that woman is cooking with? Take a careful look at the movie next. It shows atmospheric motions. This is produced at the National Center for Atmospheric Research. If we focus on East Asia, all it takes is about 3 to 5 days for air to hurtle across the Pacific. And I myself have made numerous measurements on aircraft. So while the Chinese are sending their gift to us in the US, we pretty quickly transfer that gift and send our own to Europeans in less than a matter of 2 to 3 days. That's all it takes for air to go across the Atlantic. So while we are doing that, the Europeans are sending their gift along to Asia. So the point here is each one of us is in somebody else's backyard. And we are not going to solve this problem by pointing fingers at each other. This is something we have to put our head together. Also look at how quickly air from Amazon, carrying all the biomass burning, can travel across into the Antarctic, all in a matter of 2 to 3 days. So there's no place in the planet which is free of pollution. So what happens to this blanket of pollutants and gases which surround the planet? Just to give you condense my 1/4 climate course into a 10-second summary, the planet's fundamental energy source is sunlight. Not all of it is absorbed by the planet. About 30% is reflected back to space. So the remaining heats the planet, and the planet in turn gives off this energy as infrared or heat radiation. Okay? It's this heat radiation which is trapped by this blanket of greenhouse gases. So in a sense, how does a blanket keep us warm on a cold winter night? It doesn't give off any heat. It just traps your body heat. That's exactly how the greenhouse gases warm the planet. It traps the infrared radiation, which would have otherwise escaped to space, so not as much is escaping as is coming in. So what does the planet do to restore balance? It heats up. We know hotter bodies emits more radiation, so it gives off more energy to bring the system back to balance. So it's this fighting for imbalance is what we are talking about in terms of climate change. And we had for a long time known carbon dioxide is the major greenhouse gas. And there is a problem there. We are so fixated on CO2, we are forgetting some low-hanging fruits. That's going to be the thrust of my talk. I myself stumbled onto this 35 years ago. I was a refrigeration engineer in India before I came to US. And the paper by Molina and Rowland talking about the CFC effects on ozone alerted me, so I started looking into the greenhouse effect of the CFCs. I was alarmed to find that one molecule of CFC has the same greenhouse effect of adding 10,000 molecules of CO2. Here it is, as human beings, we have synthesized an enormously efficient super greenhouse gas. It turned out after that, within a matter of 5 to 7 years, as a small group of us had discovered over 24 gases we were putting into the atmosphere. So collectively then, this was a paper in 1983. Later it became a WMO report, set off the stage for IPCC, where we concluded non-CO2 gases contribute as much as CO2 to the greenhouse forcing of the planet. Okay? And central in that finding also brought chemistry intricately with climate. So it was not a problem of physics, it was a problem of physics and chemistry. And the hydroxyl radical played a central role, and I'm not going to get into that. But ozone, we think of as a pollutant, not the stratospheric ozone. Ozone in the troposphere is a major greenhouse gas. And now I'm showing in the IPCC report, they basically confirmed our finding. What you see as the red, okay, is basically how thick the blanket is getting. Mind you, nature gave us a blanket, water vapor, CO2, they're all powerful greenhouse gases. All we are doing is making the blanket thicker. And the IPCC finding basically shows the greenhouse forcing as of now, 55% is due to CO2. The remaining 45% is from these other gases, methane, nitrous oxide, halocarbons, tropospheric ozone. I'm not going to talk about the rest, I'll come to that next. So basically then, we got curious to see when are we going to see this warming. And I know many of you have sort of followed this problem in the last 4 or 5 years. I just want to point out scientists, we were aware of this at least 30 years ago. And look at how we started, that's my paper in 1980. We already say the possible climate effects of large increase in CO2 would constitute one of the most important environment problems. So this was known, okay? In that paper, we were interested to see how large and how soon, when are we going to see this warming? It was basically a statistical model study, and it said we should see the warming by year 2000. So this prediction was made nearly 30 years ago. And I was sure our prediction was wrong, and unfortunately it turned out to be confirmed by APCC. And you can see the noise in the record. That was what we quantified in our 1980 study. It's not a monotonic warming, there are ups and there are downs. What you see is the last 70 years, the signal coming out of the background noise. This is what we had proposed. So now the question is, where do we stand now in terms of how large that warming is? Let's start with IPCC again. So they basically say we have trapped 3 watts per square meter. This is not the future. This is already the gases which are there, okay? What does that mean? That energy trapped is equal to, when you integrate it with the meter squared per square meter of the Earth's surface, it's 1,500 terawatts. Compared to that, the energy consumption, 13 terawatts. So the question is, why is the warming much larger than what it is? Okay, because the energy we are trapping is huge. And mind you, the numbers here is within 5 to 10% according to IPCC. There's not a whole lot of uncertainty because I'm not talking about the future. I'm talking about we already made the blanket thicker, okay? And I spent the first 10 years of my career finding out the thickness of the background atmosphere. That's about 135 watts per meter squared. So we have made the blanket about 2.5% thicker. And we know that. There is a good metric for precisely that. So how much should heat the planet? Again, what IPCC says is that the planet can get rid of about 1.5 watts per meter squared, slightly less, per degree warming. We have trapped 3 watts. So the heating, according to IPCC, should be about 2.4 degrees. But then there's not a single value. Our uncertainty in that is so large. So it's really a probability distribution. The mean is about 2.4 degrees. So the main point I want to make, given the thickness of the blanket, and given the sensitivity of the climate system, as IPCC asserts, we should have already seen 2.5 degree warming. But what we have seen is only 1/4 of that, 0.6 degrees. Where is the remaining warming? This is what I'd spent my time, and as several of my colleagues, There was an incredible sessions here organized by the chemists on this issue. And what I've drawn in that curve is several icons which would fall as the planet warms. Okay, these are all taken from John Schellnhuber's paper. The Arctic sea ice and the Himalayan glaciers are the two I'm going to focus on. So now the question is, where is the remaining warming? Okay, so I'm going to show you some data, but basically that by sheer dumb luck, as we were adding these greenhouse gases, we are also putting particulates in the air, okay? And these act like mirrors. So the blanket, we have made it thicker, and we have added mirrors on the blanket, so they reflected sunlight and sort of provided a mask. I don't consider it as an offset, it's really a mask. The reason is the lifetime of these mirrors is of the order of a few weeks or less, compared to hundreds to 1,000 years for CO2. So that mask can quickly be removed by cleanup air pollution laws, and then we will see the true nature of the greenhouse warming. Okay, so this 2.4 degrees is waiting there to happen. How do we know this? So this was really thought about, this mirror sulfates by Charlson and several others. We have known this for, again, 20, 30 years, but we've been looking for it. And I started out my career as an engineer there in physics, so I don't believe anything until I can touch it, feel it, or smell it. In this case, I could do all of them. So that was the experiment we did from Maldives, looking for air pollution from India, and you can see the vast amount of brown cloud. This is what we saw in the Arabian Sea, the entire Indian Ocean, North Indian Ocean, filled with these brown clouds. And there you see, it was really a joint work between Americans, Europeans, and India had large contingency. So you can see electron microscope pictures. So the top one you see is what, the anthropogenic particles from Northern Arabian Sea. And then, sorry, this picture is a little bit inverted. And on the left one is where you see the particles from Southern Indian Ocean, this spherical looking. So we had to be almost away for by 3,000 kilometers to get away from pollution. So that's how far it traveled. And the other surprising, we will remember looking for mirrors which were reflecting sunlight. There was a huge surprise waiting for us. And the top one you see the chemical composition. This was really done by varieties of groups. And the sulfates are the mirrors, but we did see them. But on top of that, we also saw a huge amount of black carbon. What is black carbon? It's basically the stuff you see coming out of diesel, or trucks, or smoke, etc. Okay? And we had on a ship spectrometer, and we had direct evidence for this effect of the mirrors. And you can see the direct light, this is the ship, we'll have the instrument looking at the sky, the ship will go in and out of the pollution. And you see the direct sunlight is cut down by almost 30%, but then the scattered sunlight is enhanced, that's the diffuse polluted. So when we add the two, we had the direct evidence for the amount of dimming at the surface. What was the surprise was, first of all, the dimming at the surface is a factor of 5 to 10 larger than what models had expected us to find. And the reason was the black carbon. The black carbon, by absorbing sunlight, was cutting down sunlight reaching the ground. So now let's go back to the blanket metaphor. So we have the greenhouse gases thickening the blanket, trapping infrared heat, and we put mirrors on the blanket, that is the sulfates, reflecting sunlight. On top of that, we filled that blanket with this black dust. It was absorbing sunlight and directly heating the blanket, okay? So it was a complex mess we found. So when we synthesize all this with satellite measurements, ground-based measurements, and aircraft measurements, what we found was this. There was the greenhouse effect is uniform, almost uniform, whereas the aerosol effect has made this blanket sort of patchy. And you see the major regions. The blue at the surface is the dimming. And what we suggested then was India and China had become dimmer by about 7 to 10%. And this was later confirmed by Indian scientists and Chinese scientists by publications. Okay? And on top of that then, the blanket heating, you see there on top of that, And the magnitude of that over India and China is about a factor of 5 larger than the greenhouse forcing. So regionally, there's a huge, major things happening on top of this overall warming by the greenhouse gases, okay? So the dumbest thing we can do to the planet is cut down sunlight, because it's sunlight which gives us precipitation, evaporates moisture from the ocean, then what goes up falls off as rain. So you expect you cut sunlight going into the ocean, you're going to cut rainfall, and that's what most GCNs show. And in fact, this shows the 50-year trend over India. This is a paper we published on the right-hand side. The red regions are where India's getting dry, less precipitation. IPCC confirmed that. But now more recently, Indian meteorologists, this was a paper which came out last week, basically showed throughout India moderate rainfall is decreasing. And this is all last 50-year trend, okay? Next is, sorry. I didn't set the stage for this. I'm not sure if I'm going to be able to go back. Yes. Yeah. What we wanted to see was this heating. That heating we are seeing for the black carbon absorbing in the blanket was so large, we had to directly see it. And the only way we could do that is come up with 3 aircraft flying simultaneously, one above the cloud to measure the sunlight going into the brown cloud, one at the bottom of the brown cloud to see how much is coming through so we can directly measure the heating. And let me just, yeah. So this aircraft, it's about, 2 meters long. It does make that louder sound. So it's sort of launched manually, but once it's airborne, it's completely autonomously controlled. So for the first time, we had precise capability to target our aircraft, see the next as it goes through a cloud. So we could really penetrate exactly at the point in the cloud where we want this to go, okay? So at the same time we were doing this aircraft experiment, NASA had launched this satellite called Calypso, and that shows the thick 3-kilometer brown clouds surrounding the Himalayas, both from the Indian side and from the China side. And the heating we measured it was increasing the background solar heating by about 50%. I'm not talking about 1 or 2%, close to 50%. And that was the measurement from the Italian group on Pyramid. Right at the base camp of Mount Everest, they were finding as much black carbon as I would find downtown Los Angeles. Okay, so we know now black carbon is there, and this was the paper just published because what we had speculated was the reason the glaciers are retreating. The glaciers already knew that it was because the air was warming enormously large, and we suggested half the reason the air was warming was from black carbon. So that was again confirmed in a paper using microwave data, showed that the whole Indian region, mid to upper troposphere, is heating much, much larger than the surface air. So the last one on the black carbon is, what happens when this black carbon settles down? The snow and rainfall removes it. Unfortunately, this black carbon is deadly, whether it's in the air or it's on the ground. It makes the snow dirty and makes the snow absorb more sunlight. And this was a paper done by Flanner and several others. We saw together the black carbon heating the air, falling on the snow and the heating is roughly, we said, half the reason why the Himalayan glaciers are retreating at an alarming rate. And we had a paper by Dr. Sorby Menon suggesting something similar. I'm going to skip this. So why is this issue with the Himalayan glaciers? Of course, it provides the headwaters for all the major rivers in India. So it's called the water fountain. Honestly, I think if there is a major disaster waiting to happen in the next 20, 30 years, it's the Himalayan glaciers disappearing. So going back to this, so where do we stand in all this? So the greenhouse forcing is about 3 watts. We should have committed the planet to 2.5. We are only seeing about 1/4 of that, about half a degree from IPCC stored in the ocean, and the remaining, according to ours, has been masked by aerosol cooling. So that's the good news and the bad news. So let me now come to what are we doing, okay? First, let's look at the CO2 problem again. We are putting about 8.5 gigatons per year CO2. At fixed emission, by 2030, we would have added 108 gigatons. even if we reduce the emission by 50%, let's say Copenhagen agrees on that, by 2030, we would still be adding 80 gigatons. So the 2.5 warming would go towards 3. So we are not talking about reducing the thickness of the blanket. We're only talking about reducing the rate at which this blanket is going to get thicker. So we are stuck with already this thicker blanket, okay? So the CO2 policy is not going to, we have to do this just to prevent the problem from getting worse. Our question is, how do we get out of the mess we are already in? And so this is where several of us are suggesting the short-lived climate warming agents hold the key. And look, the left bar is what the committed warming 2.4, and the 1.3 is what we are seeing, because the mask has masked about 1.1. What we are right now doing with our air pollution laws, cleaning up SO2. I'm not claiming we should keep the sulfur and get drained by sulfuric acid, but we have to understand every time we remove a ton of SO2, we have to remove hundreds of tons of carbon dioxide to balance it, which we are not doing, okay? So we are sort of accelerating towards the 2.4. What we are suggesting instead is, if we focus on black carbon, if we eliminate the black carbon, which is of course a theoretical calculation, my own estimates show we would cut down that warming from 1.3 to 0.6. But there is a huge uncertainty. The IPCC values could be a third of that. And then ozone will bring it down to by the factor of 2. So in terms of the low-hanging fruits, to figure out how to get out of the mess we are in by the blanket thickening, we got to focus on the short-term warming agents. That by itself is not going to solve the problem. We still have to reduce CO2, but we ought to bought ourselves some time, somewhere between 10, 20 years' time. Towards this goal, I'm just going to quickly talk about what I'm personally trying to do. I think this is what urged by us, our chairman. I believe each one of us have to take this problem in our own hand, start individual actions. So towards this, we have started a project called Surya. And just to orient you, what we are basically trying to cut down the biofuel emissions, okay? The top one shows a simulation by Greg Carmichael of the black carbon over India and China. And the bottom one shows how India would look just if we eliminate biofuel cooking. In other words, not eliminate the cooking, the people have to live, replacing cooking with biofuels, with biogas and other smoke-free cooking. And so we've started this in 2 regions in India. We're targeting a population of about 20,000. So hopefully we will create a black carbon hole, okay? And we want to make the most detailed measurements to see for ourselves how much of a warming are this biofuel contributing. Our models suggest a large amount, but we want to show it. So we have started a pilot project in which you see that woman holding the Philips stove, which is supposed to cut down the emission by a factor of 2 to 3. And the other one is a solar lamp. We are replacing the kerosene lamp, which is a source of black carbon solar lamp. And it shows we're going to set up instrument towers to make the careful observation. It's really an active experiment, okay? And in this region, we are talking to NASA group to monitor this village at a high resolution to see if we can see the effect, okay? So it's a sort of a 2-year project. We're also going to use cell phones as a way to collect data. As you know, there are about 4.5 billion cell phones. It's an enormous platform to collect data. One thing we are starved in climate science is lack of data. So it's a question of using miniaturized technology, and we are pushing that too. I just want to conclude with this. I know we are focusing on high-tech stuff. It was really clearly, beautifully shown in Bill Shamiri's talk about the population. We're going to reach 9 billion. And those who claim that we are going to prevent this exceeding the 2-degree warming by cutting greenhouse gases by 50%, it's not all clear to me how we are going to cut nitrous oxide. The world population is going to go to 9 billion. And I feel it's key that we want to work on this. 4 billion, we are still trying to climb up that energy ladder to see if we can give them sustainable way. And that's what we are trying to get started in Surya. Thank you.